Okay, I would like to call Dr. Mohammed Al-Abri, and also we have with us Dr. Imad Al-Qarabliya. Okay, so welcome to the session 6B about wastewater management. The organizers and the scientific committee called prominent scientists, researchers, experts in diverse aspects of wastewater. As we all know, non-conventional waters are gaining importance in all the world, but mainly here in GCC and the MENA region in overall. Mainly wastewater treatments and reuse is also one of these types of wastewater that is expected to alleviate water scarcity in the region and also contribute to the sustainable development through circular economy implementation. I am Dr. Youssef Brouzine. I represent IWMI, the International Water Management Institute in the Middle East and North Africa region. And we collaborated with various organizations and institutes in the region previously. We collaborated with ACWUA, with the Arab Water Council, FAO, ICARDA, a lot of organizations to look at the wastewater value chain prospects in the region and also situation in the region. And through this research, specifically a project called Rewater MENA, we found that a lot of things have been achieved in this field, especially here in the GCC, where we have the highest percentage of treatment of safely treated wastewater. But the average for MENA is around 60%. So 60% of wastewater, municipal wastewater, is treated safely in MENA, with obviously high percentage here in GCC and other countries like Jordan, like also Egypt, etc. The reuse part is another story. Obviously less, we have a smaller average in the region. And this is basically for many reasons. One of the reasons it's mainly about the treatment processes. So from engineering perspective, we need to advance the treatment process that we are using in the region. One of the other bottlenecks or challenges is about the environmental aspects of reuse. That will definitely hinder and make the developments more difficult. One of the other, let's say, losses, since we don't reuse much of our wastewater, is the energy that we can recover from this wastewater if it is fully reused. And in addition to the financial and the business models that are in place in the region around the reuse that are not enough sustainable, viable, so a lot of innovation is needed. And by the way, these are the aspects that we'll cover in this session. So I congratulate the scientific committee for collating these speakers and also covering these bottlenecks that are very important where innovation is needed. So we will listen to the first speaker, who is Dr. Abdullah Al-Ma'touq from Kuwait Institute for Scientific Research. Obviously, Dr. Al-Ma'touq has a long biography, but I would like to mention that he is an associate research scientist at the Water Research Center of the Kuwait Institute for Scientific Research. He has a bachelor in civil engineering from Kuwait University, master degree in water research from the University of Birmingham, and PhD in civil engineering from Cardiff University. Dr. Ma'touq is working in the area of generating energy from wastewater through electrochemical systems and anaerobic digestion. And his intervention, that will be around 15 minutes, will be around electricity generation and industrial wastewater treatments using microbial fuel cell. Dr. Ma'touq, please.
صبحكم الله بالخير جميعا. بسم الله الرحمن الرحيم والصلاة والسلام على أشرف خلق الله سيد المرسلين سيدنا محمد بن عبد الله وعلى آله وصحبه أجمعين. Good morning everybody, and first of all I would like to thank the Gulf Water Science and Technology Association for their hospitality and the opportunity to present our previous our recent research on microbial fuel cell. My name is Abdullah Al-Matoug. I'm Associate Research Scientist in Water Research Center at the Kuwait Institute for Scientific Research. This is the overview of my presentation. We will start with a brief introduction about the energy in wastewater and how can we harvest energy from wastewater. And then we will move to the aims and objectives, then materials and methods, results, and finally the conclusion and recommendation. Well, I will start my presentation with a question. Why do we have to implement such a research in this field, or in Kuwait especially? Well, the answer is two reasons. Firstly, Kuwait's vision in 2035 to provide 15% of the energy required in Kuwait from sustainable resources. Plus, the second one is the population growth in our countries, which leads to make a stress on our water resources. And as a result, we will generate more and more wastewater every single year. As a result, we will treat that huge amount of wastewater. To treat this amount of wastewater, we need energy. So based on our recent literature, we found that between 3 to 5% of our global energy consumption was used in water industry sector. By the way, to treat 1 cubic meter of wastewater, we need between 0.5 to 2 kilowatt hour. So you can imagine how much energy we need to treat all that amount of wastewater. On the other hand, energy is a valuable resources of, wastewater is a valuable resources of energy. Do you know that wastewater contains 3 different types of energy? It contains chemical energy, which is the energy that is hidden in the chemical compounds and the bonds between the chemicals molecules. Plus, we have a thermal energy, which is the energy that's available as a heat in wastewater, and we can extract it. Thirdly, and the kinetic energy, which is the motion of wastewater from one location to another. The organic energy in wastewater is approximately 5 to 10 times the energy, higher than the energy is required to treat wastewater. So there is a massive amount of energy in wastewater. Each 1 gram of COD contains 16.1 kilojoule. So each kilogram of COD can produce between 2 to 4 kilowatt hour. There are different technologies that we use to harvest energy from wastewater, such as anaerobic digestion and the bioelectrochemical system, which contains microbial fuel cell. Microbial fuel cell is a unique technology, can convert the chemical energy in wastewater into electricity and can be used directly in different applications. The microorganism in microbial fuel cell act as a biocatalyst, which means that they can extract the chemical energy from the bonds and from the compounds and convert it into electricity. The chemical energy accumulated in the chemical compound can be harvested using the oxidation reduction reactions in microbial fuel cell. So microbial fuel cell contains 2 main chambers, the anode, which works or which operated under anaerobic condition, and the oxidation reaction takes place, plus the cathode, which works under aerobic condition, and the reduction reactions takes place there. Our aims and objectives, of the study, the main aim is to investigate the treatment efficiency and energy generation from various industrial wastewater streams using microbial fuel cell. The study specific objectives, first, to design operate and install a pilot-scale tubular microbial fuel cell. Secondly, to assess the efficiency of MFC in treating wastewater. Thirdly, to evaluate the generated energy from microbial fuel cell. Our methodology that we use to execute this project is, first of all, we have to select what kind of industry we are looking for. So we did a basic survey in Kuwait to identify what are the major industry in wastewater. And based on our results and the different literature available, we found that there are four main industries. First, the petrochemical industry. Secondly, the dairy industry. Thirdly, we have a soft drinks industry. And finally, we have the detergent industry. From each industry, we just selected 2 factories to represent this industry. And based on the characterization of each industry, we have selected 4 factories to represent the 4 industry. And the selection was based on the COD concentration, the nutrient availability, the conductivity, and the pH. Secondly, we designed 9 tubular microbial fuel cell. And we ordered all the raw materials. Every single piece was fabricated at the Kuwait Institute for Scientific Research. So we have divided the microbial fuel cells into 4 main groups. Each group will be targeted for a specific industry. This is the picture on the right shows the design of microbial fuel cell. We used a PVC pipes with a length of 75 centimeter with a diameter of 10.5 centimeter with an overall volume of 6.5 liter. We used a real wastewater from the activated sludge to inoculate the microbial fuel cell or the bacteria in the microbial fuel cell. We used a carbon approach anode and connected to a titanium wires, plus we use a carbon cloth cathode. The PVC pipes had holes of 1 centimeter. The main idea of the holes to keep the industrial wastewater in contact with the cation exchange membrane. And also we use a CE cation exchange membrane, which is wrapped around the pipe. And on the top of that, we use a stainless steel wire mesh. The main idea of the stainless steel wire mesh is to collect all the electrons that are produced during the electricity production. As you can see, we have 9 MFC, and each 2 MFC was fed with a specific industrial wastewater. The MFC was connected to a resistance box, so we can manipulate by the load, so we have to select different loads, and it's connected to a data logger which record the voltage, the produced voltage, and it's stored in a BC. The results, all the MFC were continuously operated for more than 120 days. And thanks for God, we haven't had any major issue with our microbial fuel cell. We have just minor issues such as the blockage of the pipes, because all the industrial wastewater was fed to the MFC without any filtration, so they were a raw industrial wastewater. All the MFC generated a maximum open voltage. By open voltage, I mean there was no load, so this is the maximum the MFC can achieve. So the dairy wastewater achieved the maximum or the highest open voltage, which about 0.62 volt, and followed by the domestic wastewater, 0.5, then the detergent, 0.49, soft drinks, 0.46, and finally the petrochemical industry. By the way, petrochemical industry, we had a major issue with the characterization of the petrochemical waste. It contains different toxic materials, such as anti-foaming agent, corrosion inhibitors, and demulsifiers, which could inhibit the growth of bacteria and the activity of the bacteria, and that which led to the low the generated voltage in these MFC. In terms of Coulombic efficiency, by Coulombic efficiency, we mean that the amount of electrons we harvest from the industrial wastewater and can be used for electricity production. So the higher CE, the high MFC efficiency. So if we can compare our CE was too low in this study, so it's between almost 0 to 2.9. 0 was for the petrochemical industry, and the maximum 2.9 was for the soft drinks, I guess. So if we compare our results with the different literatures, it seems that our value is in line with the different literature. In some cases, our values are even higher than a small-scale microbial fuel cell. By the way, I have to mention that we are using a real wastewater, and it's without a filtration. So it's very complicated. If we can just convert it to synthetic wastewater, for sure, we will have a high efficiency of the MFC. In terms of the power density, the dairy wastewater was able to produce...
1 minute, please.
4 minutes?
1 minute.
1 minute, sorry. So our highest power density was achieved in dairy wastewater, and each cubic meter of wastewater can produce between 86. I have to go fast. In terms of wastewater treatment, the MFC achieved a very high wastewater, or the efficiency of treatment of wastewater, especially with the COD removal efficiency. I have to go fast. In terms of nutrient availability, the MFC were not able to remove any nutrients such as phosphorus and nitrogen. By the way, phosphorus was increasing in all the MFC because under anaerobic condition, bacteria try to release the stored phosphorus in their cells, so we have a high phosphorus as the effluent. In terms of nitrogen, they followed the same, except for domestic wastewater, which was operated as a control. In terms of internal resistance, the MFC had a high internal resistance, and that negatively affect the performance of microbial fuel cell. And the conclusion and recommendation, I think the main idea of this project is to characterize and identify what's the best streams that can be used for microbial fuel cell. And it seems that dairy industry was the best stream that can be used for microbial fuel cell. The recommendation, we have to improve the performance of the MFC by using more efficient self-generating catalyst in the cathode. Plus, we have to enhance the design so we can improve the efficiency of the MFC. And also, we can integrate the MFC with different technologies to provide a better effluent quality and more sustainable system. And thank you so much.
Thank you. Thank you very much, Doctor, for this interesting research. An area where we need more innovation to unlock more potential for reuse, especially in the energy perspective. And I personally appreciate the fact that you tested this technology over different types of wastewater, which is really, really interesting. Thank you very much. I'm sure there will be a lot of questions at the end of this session. So we will go now to the second speaker, who is going to speak about advanced wastewater treatments using functionalized membranes. And this will be provided by Dr. Mohammed Al-Abri, who is Associate Professor in the Petroleum and Chemical Engineering Department in Sultan Qaboos University in the Sultanate. Please, Professor. So Dr. Al-Abri is a leading figure in the nanotechnology, water treatment, membrane technology, mashallah, a big bio. So he has more than 35 major research projects in these fields of nanotechnology, water treatment, membrane technologies, more than 95 journal papers, and he received the first Arab Water Council Award for creativity and innovation in 2021. Please, Dr. Al-Abri, 15 minutes.
Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. First of all, I would like to thank Gulf Water Science and Technology Association and Prof. Walid for the invitation. Thank you very much. Also would like to thank Oman Water Society as well. It's a pleasure to be standing in front of all of you and give a brief talk about the work, a bit of the work that we do in the Nanotechnology Research Center. We are basically a center that is working on the applications of nanotechnology in 3 research areas: water treatment, oil industry, and renewable energy. And today I'm going to talk very briefly about a bit of the applications in the water treatment, specifically in the membrane part. Nanotechnology Center was established in 2017. Last week we reached the milestone of 100 publications since 2017. We also have four technology patent applications since then, and we are working on more of those. Of course, since we are a research center university, we do a lot of capacity building, and that's why we always have PhD and master students with us. We currently have 5 PhD students and 4 master students in the center, as well as other things as well. So before I talk about the membrane part and the functionalization, I would like to talk a bit about some of the leading work that we do in the center. We do a lot of work on water treatment using membranes, and one of those is membrane distillation for hypersaline. This is a project that we have with the Ministry of Agriculture and Fisheries Wealth and Water Resources in Oman. And we have a pilot plant where we desalinate brine water coming from an RO desalination plant, from inland desalination. We also we do membranes for medical use, and we have a patent application on catheters trying to reduce the infection rate from using the catheters in hospitals. We recently, 2 years ago, we applied for a patent on membrane recyclability. Of course, we rely on reverse osmosis in almost all of our desalination. Probably only maybe Emirates still rely heavily on MSF and thermal desalination. However, we have been transitioning towards reverse osmosis, and with reverse osmosis, we have a lot of RO membranes that we throw away. And so with this work, we recycled the RO membranes so that we can use for wastewater treatment. And we are currently actually trying to move forward and repurpose this. We reapply these again for desalination as well. This is the next phase of our work. We are working on nanosensors for water treatment and sensing of any kind of fouling. And this is a patent that we are currently working on. We are also working with capacitive deionization for brackish water desalination, and we have 2 patents on this. So very briefly on all of the work that we do in Nanotechnology Research Center. So before we talk about membranes, we need to talk a bit about wastewater. In Oman, it's not really the usual wastewater that we really need to think of. It's also the produced water, but I'm not going to talk about produced water. I will talk about other industrial wastewater, because not all of the water is domestic or municipal wastewater. There are a lot of other sources of wastewater. And these are very difficult to work with. And also, it's not easy to work with or determine what exactly is the best treatment for it. Probably we need a lot of different treatments for it. And just to stir the pot, I know there are a lot of people here, definitely a lot of people here who are advocating using treated wastewater for agriculture purposes. That's fine, but also we have a problem with emerging contaminants, or what we call persistent contaminants. And these are a lot of studies that happened. We worked with groups from South Africa and from other areas where there is a lot of persistent contaminants that the usual conventional wastewater treatments cannot remove. And these amounts are very minute, and usually for, as you can see here, for the water quality, we just look at it as a number rather than a type. What type of contaminants are there in the treated wastewater? So a lot of antibiotics, a lot of medical, even caffeine is there in the water. In South Africa, our team collaborators from South Africa, they even found a lot of caffeine and other endocrine disruptors in the Arctic, where the penguins, they had a lot of fatalities there because of these endocrine disruptors chemicals. And this is a study that was done in China for 335 emerging contaminants, mainly pharmaceuticals. And as you can see, it's not really easy to treat those with domestic or municipal wastewater treatment. Some of those treatments only remove 10 to 15% of those. And again, 1 microgram or 1 milligram per liter is a lot for these. They are very toxic. So moving forward, these are membranes. Of course, the usual membrane that we talk about is the typical one, which is the pressure-driven. So we apply pressure on one side, and then the water will pass through the semi-permeable layer or membrane and will not allow the other contaminants to leave. And that's why we have these kind of differentiations from microfiltration to reverse osmosis. However, there are a lot of other membranes and technologies that are not really here. We talked about membrane distillation yesterday. There was a talk about forward osmosis. We talked about pervaporation membranes, microbial biofuel cells as well. They use membranes. Even capacitive deionization, we can apply membranes in there. Of course, not even talking about electrodialysis and electrodialysis reversal and all of those. So what we have really, and I'm not really going to talk about this in details because it requires a lot of time, but we rely on membranes in almost all of the desalination and water treatment we do. Whether it's in the wastewater treatment, we talk about membrane bioreactors. In desalination, we talk about reverse osmosis and ultrafiltration, microfiltration for the pre-treatment. And there was a lot of talk about nanofiltration for a pre-treatment or a good desalination for brackish water, although it's really not taking any push in that regard. But we also have a lot of problem with fouling. So different types of fouling depending on the water source. Biological fouling is the main one for reverse osmosis and seawater desalination. Biological fouling and organic fouling is a main issue with wastewater treatment. And that's why what we are with basically what we do is said, why not functionalize these membranes with nanomaterials so that we can reduce the fouling or at least increase the flux and the rejection. So with the nano applications, we have a lot of applications. We can use nanoparticles with the membranes as adsorbents or functional membranes for separation. Fenton catalysis, nano disinfectants are very good also and very strong, and a little bit about photocatalysis as well. So we need nanotechnology because it basically, compared to other technologies, it doesn't produce secondary pollution, or what produces benign secondary pollution that we can put in the environment without any harmful effects. It's also low cost, has high efficiency, and it's environmentally friendly. And so when we talked about membranes, a membrane is not only, we don't really look only at the rejection and how much we produce, water we produce. There are a lot of properties that are important for the membrane. Permeability is important. The mechanical strength is very important. Thermal stability, fouling resistance, rejection, pore structure. And also photocatalysis, which is quite new, trying to also have photodegradation as well as rejection of organic matter. And this is why in the center we've worked with different polymers for the membrane network and structure, but also we use different nanomaterials for that, starting from carbon nanotubes, where we have a patent for this. Reduced graphene oxide is another thing. Zinc oxide and titania and silver as well. So we use different kinds of treatment. And so this is one of the first patents that we have done. We know that cotton is highly hydrophilic. It really likes water, so it absorbs water a lot. And what we did is we grew nanoparticles at the surface of the cotton. And so we made it hydrophobic instead of hydrophilic. And that made it oleophilic. And so what we've done is we've made this cotton highly oleophilic. We put it on an oil spill with water. And what it did is it absorbed the oil and left the water. And this is a very good for environmental remediation for any kind of oil spill. This is the only work that we have done for super hydrophobic. The other work we do is on super hydrophilic, basically, so that we have higher passage of water and no passage of any other kind of contaminants. Another work that we have done, and this is for produced water from the oil industry, is different nanomaterials, and here we have the hydrous manganese oxide. And you can see that with the hydrogen or the hydrous manganese oxide, we had close to 100% removal of the organic matter, but we also have higher water production. So that's the good thing is we have higher water production, which is fantastic, higher permeability, but also we have higher rejection, which is good in both ways. Another study is photocatalysis. Photocatalysis is different from other treatments. It's, what we need is an energy source, and previously it was ultraviolet, which is not really a good source because it's expensive and it's very dangerous. What we use here is solar light, a normal solar light. And what we need is a very basic contact between the nanomaterials, the photocatalyst, which is a semiconductor like zinc oxide or titanium, but titanium is not good for solar light. Zinc oxide mainly. A contact between the organic matter at the surface of the nanomaterials with the solar light, and we have reactive oxygen species, energy holes, hydroxides, and all of those, and these will react with the organic matter, degrading them into carbon dioxide and benign acids. And with that, all kind of organic matter, instead of rejecting it and going into the reject, it's actually degraded and completely removed from the water.
1 minute.
Okay. Oh. And so this is what we have done, one of the studies in the marina for photocatalysts. This is with a group from agriculture, College of Agriculture, from Marine Sciences. And we had a very good results in that, no growth of any kind of macromolecular or micromolecular. Another study for natural organic matter, and we got more than 80% degradation, whether it's rejection or full degradation of the natural organic matter. And also we had a higher water flux. Another study that we have done is grown zinc oxide nanorods on the membrane matrix, whether it's at the surface or inside. And we actually got amazing results, because again, one of the major 80% of the problems of reverse osmosis is biofouling, bacterial growth. And what this did is, with the zinc oxide growth on the membrane matrix, even after 48 hours of operation, the bacteria is actually dead. It's not only present and it doesn't grow, it's actually dead at the membrane surface. And this is what we have from the microscope. The red dots means that the bacteria is dead. It's non-functional, while green is alive. And so these nanobacteria, they don't only remove the bacteria, they are also very good in disinfection. Unfortunately, even of those, we are really on the second part of the technology readiness. We are still in TRL4 to TRL6. And this is because we have a problem with the cost uncertainty in the cost. We don't know how much will this cost if we are applying it in the industry. There is also a lot of competition with conventional technologies. The current companies that we have, they have extensive experience in conventional, and of course they don't really welcome any kind of competition. So you need a lot of investment, initial investment, so that you can really push towards that, and other environmental considerations as well. And probably I will miss this, but also the problem is from our side as researchers and academics. We really concentrate on the fundamentals. So from this study in photocatalysis and water treatment, you can tell that almost all of the publications are in the main fundamental capacity building. Very, very few in pilot studies and reactors, which is not really good if we want really to apply this in the industry. And probably I will miss this. That's why if we really want to go forward, then even if this technology currently is not suitable for the mainstream, it's not suitable for desalination of seawater, we rely on seawater desalination, or these, we can look at the niche market, the small markets, industrial wastewater here, and this dairy wastewater and all of that. And why not apply it for those? Because they are very competitive in that regard. Just like for osmosis is very competitive for produced water as well. And it's not really good for highly saline water. We need to look at the comprehensive cost analysis as well. We say that it's cheap. We know that it's cheap in the lab. But we don't know what are the other requirements that the industry would require. So we need more comprehensive cost analysis. And we need large scale and long scale, long time frame research applications. And this is why, this is the last one. This is why in the lab we are currently looking at the hybrid system, where we will have capacitive deionization for the desalination. We will have membrane technology for the removal of organics and inorganics. And we will also have photocatalysis with the nanomaterials for the degradation and for biocidal treatment. And basically what we have is, in the energy side, renewable energy, good, and 3 different technologies in one: capacitive deionization, photocatalysis, and membrane in one big system for complete removal. And this is a very good for small scale, comprehensive for inland desalination. And with this, I end my talk. Thank you very much.
Thank you very much, Dr. Mohammed Al-Abri. Very interesting research. Again, a lot of results, and you are definitely touching on an aspect where we need more research, obviously, membrane-based treatment of wastewater. And I can see a lot of promising results there that we will definitely discuss in the Q&A session. So thank you very much again. So now we will go to the last presentation of this session, which is again about a very, very interesting aspect, which is the business models for small-scale decentralized wastewater treatment and sludge management in a country where a lot of research is ongoing about this track, the Kingdom of Jordan. And it's going to be Dr. Imad Al-Qarabliya, Professor of Water and Environmental Economics from the University of Jordan. So a lot of things to mention about your experience, but I can say that Dr. Qarabliya has more than 25 years of experience in water resources management, irrigation improvement, focusing on the formulation, identification, implementation of evaluation studies, financial modeling of irrigation infrastructure and water resources management in general. Dr. Imad, please, 15 minutes.
Yeah, thank you. I would like, first of all, to thank also the Water Science and Technology Association of the Gulf, and also a sponsor, donor, and Dr. Walid Al-Zubari for allowing me this opportunity to participate in this conference. I will not talk technical about the wastewater treatment technology, and this is not my field. My field is related to the people, to the business. Is now, in general, most of the wastewater treatment project in the world is financially infeasible. So this means that we have to find another way to justify investment in the wastewater treatment, and we use the economic and social dimension to justify the investment. In our thought, now, at least in Jordan, according to the, how can I go back? To the National Development Goal, SDG 6.2 and 6.3, that no one should be behind regarding to the wastewater connection and treatment. So I will go back from the first presentation. I don't know how. Red one is go back. Yeah? Okay. So this is the content, but the picture can tell you that in some cases, in some communities, it's hard or difficult to connect the people to the centralized wastewater treatment due to many reasons, either topography, either scattering of the houses, remote area. So the thought of using decentralized wastewater treatment. And decentralized means that we need to cluster the community to the either to the size, or the decentralized can be used for individual houses, individual economical unit like hotels, etc. Could be also for industrial, could be also for large communities. They agree that a community with less than 5,000 population equivalent with some specific characteristics of the topography can benefit from decentralized wastewater treatment. So the importance of the decentralized system is the environmental protection, and we find in many areas that groundwater vulnerability map shows that these areas or these communities are endangered by using cesspit instead of connecting to the sewer system. Also, public health, and we find in many areas that the incidence of less than 5 years old child with diarrheal diseases. So the decentralized can also participate in the reduction of diarrheal diseases of the less than 5 years old child. Also water conservation, cost effectiveness, also community engagement in the sanitation process and treatment. Also the decentralized provide the flexibility and the sustainability of the operation system. So in Jordan, at least we have an institutional and regulating framework. We have a national water strategies that aim to expand sanitation services and to improve infrastructure using decentralized system where it's feasible, focus on the efficient management, taking into account health, groundwater vulnerability, hygiene and environmental constraint, and also the decentralized can be implemented in the remote area with less population density, and also there is a standard and guideline was prepared for this decentralized. And in terms of institutionalized, Jordan is prepared, one of the countries in the Arab world that prepared decentralized wastewater management policies. And now this also policies is being also updated, also in cooperation with World Health Organization. They provide also a policy brief for the decentralized waste management. And now if we need to connect the decentralized system with SDG goal related to the 6.2, achieve access and adequate sanitation and hygiene for all. And this is word for all is very difficult. We, in Jordan, at least we said by 2030, we cannot provide sanitation services to all. Let's achieve 85% in Jordan, whereas remote and rural communities cannot be achieved. So let's concentrate onto the communities with less than 5,000 population equivalent as a decentralized system. Above that, with centralized system, lower than 100, let's leave it for the next generation. Also, the improved water quality and water pollution, and also 6 P's is the participation of the local communities. So due to the topographic, there is 5 steps to selection of the technologies that I will not going in detail it because I'm not expert in how to select the most suitable wastewater technologies according to the effluent quality, according to topography, according to the BOD, COD, etc. But there is a 5-step to select the appropriate technologies for each site or for each communities. According to the work we have 850 communities in Jordan, small communities. We identified that 85 communities are suitable to implement decentralized wastewater treatment system. Most of them are in the north of Jordan, whereas with the high rainfall and there is also a vulnerability related to the groundwater system and also related to the wastewater vulnerability regarding to the health impact. Now to the concept of business model, have 2 principles, who do what, and also the principle of polluter pay principle. So anyone who pollute the environment, he have to pay. Also, in the first question is how to run this small scale decentralized system or this small plant, which in the most cases required only 2 or 3 persons in maximum. And the second part, who will pay to cover the cost of the running, and also the question, what is the benefit of the one who run this business? He look or seek for profit. And we know that most of the treatment system, wastewater treatment system, are financially non-feasible and does not generate enough profit for operation and maintenance costs, regardless of the full cost recovery. So the objectives is to review the existing decentralized wastewater system framework, including institutions, law, rule, and regulation, and coordination, and recommendation for improvement, and provide a concise policy suggestion to enhance decentralized wastewater system. Also exploring the business model, who will do what and how. So the methodology, we reviewing of the in-depth analysis for the different business model. Selection as a case studies, in this case, we choose a village, Rasoon in Ajloon, and we conduct a more detailed feasibility analysis in terms of financial appraisal and economic appraisal of this small project. Taking into account that these communities is in a rural area, groundwater vulnerable. Also, we include also discussion with the stakeholder, how they can participate, what they're needed, and why they're afraid from this decentralized system to be in near their communities. There are concerns of odor, there are concerns of reduction of the land value if there is a treatment plant in their livelihood, in their neighborhood. So we discuss also with them the challenges and the solution to identify the challenges in legislation, in financing, in construction, operation, and maintenance, and proposing a suitable financial model for sustainability. So one of the results, in general, in Jordan, the sewer system is 68 in 2022 is the coverage, funded all of them by the government source, and also from the international donor, and also from the household water bill. Wastewater treatment and challenge. Inefficient wastewater treatment plant struggle to meet the standard. With treated wastewater mainly are used 90% for reused in agriculture, and there is some violation in some indicators. So, but this indicator can be also accepted if it's not, in term of have a long-term impact on hazard and risk. Also, the sanitation method and private system and risk area without public sewer system can use a private disposable method like cesspit, not septic tank. Septic tank is accepted as a method of wastewater treatment or collection. There's also, we found that institutional challenge in Jordan, at least the role of the institution is not clear. The ownership of the decentralized unit or treatment plant is not clear also. Maintenance responsibility, inadequate regulation and framework to monitor the effluent quality. There is also a potential or concern from the private sector engagement. The private sector is looking for profit, but they also need long-term financial viability required stable regulation and financial condition, including tariff clarity and also subsidy. We need to know in advance subsidy commitment. Also, the consumer support and willing to pay for these services, and it's crucial. Commitment of a stakeholder and to support from the institution needs and sustain revenue stream. This is an important. Also, meeting investor expectation who is looking for profit and positive cash flows. If we construct or implement this decentralized wastewater treatment plant, if the bankrupt of the investor, so we cannot close this unit. So it's the people is relying on it. So how we can behave in the term of risk of unsustainability of the investor if he is out of business. So this is one of the concern. Also, just how many? Well, let's make it two. We discuss also the type of ownership of the model, either governmental, private, full privatization, or a mixture between of them. And there is many options. The most selected option is the municipality ownership as subordinate with their companies. So from public to full privatization, and also there is the selected from the stakeholder is municipality. The summary of the business model, we need to, what is the purpose of the either collection or treatment or together, or using of the effluent, who is the target consumer, what is the strategies, public services or full private sector or mixture, organizational structure is public company, subordinated water companies, municipalities, private sector, ownership, either sole ownership or public or shared, and we found it's in, at least in Jordan, is community ownership, municipalities ownership. How much is the CAPEX or capital investment cost? How much is the operational cost? Source of finance, how we can finance this decentralized wastewater treatment plant, either build, operate, transfer, design, build, operate, transfer, designed, etc. Also, how much to set the water tariff and operational process. As a summary, we find that the average incremental cost or the cost per cubic meter. So in the business model, we are not looking how much is the IRR or the benefit cost ratio. We are looking how much is the cost of per unit of the cubic meter. So at least in our case study, the cost treatment of 1 cubic meter 0.6 JD, which is equivalent to less than $1. But the tariff from the consumer, or it's less than 0.2 JD. So who will pay this difference? Either selling from treated wastewater, subsidy, find other business related to the using of the treated effluent, or etc. Also we have studies the private sector participation and the private sector ownership, and we found that most of the business related to the, providing either service contract or performance contract is the best way to handle with decentralized wastewater system. Now I will go just to regulation, setting a standard. What is the important is we need a certification body for the wastewater treatment technologies, because technologies is wide, different technologies. For the decentralized system, we need a certification body and also amend the regulation and institutional capacity coordination and rule. And as a recommendation, establishing a monitoring body for the decentralized wastewater effluent, encourage private sector participation, considering a site-specific solution for each different communities according to their needs and topography, according to the density, etc. Also implement as a technologies, remote monitoring technologies for monitoring the effluent from this wastewater treatment plant, and also diverse financial model. Thank you for listening. So I hope that I covered the aspect quickly. Yeah, thank you.
Thank you very much, Doctor. Again, a big set of results. Designing a successful financial or business model for this kind of centers. Remote areas is very, very needed in the region. So thank you very much. I think we successfully saved a few minutes for questions, discussion, and I think the topics are very important and deserve to be elaborated more. So let me take the questions that we have, and then we will give the speakers a chance to address these questions. So we have the first question here. Do we have a mic?
Thank you, Yusuf. Thank you, the team. It's very interesting. A lot of hard work. Thank you a lot. Kuwait, did you try to do a time relation with blockage? And did you try also the backwashing or flushing to clear your holes, the membrane holes? This is for Kuwait. Dr. Mohammed, I missed at the end your slide. Is it a composite membrane or a hybrid process, one after the other? The three system with a solar, okay? And for the gentleman, Jordan, I think in order to sell your project, you have to develop some scenarios, models, okay? Financial models, 2, 3, 4 different models, to be able to sell it to either private, to the community, or even to the government. I think you need to do that before you can commercialize your project. Thank you.
Thank you very much. Let's see, do we have other questions? Yes, we have one more here.
Thank you very much. Just a short question to Dr. Abdullah Al-Bato. I saw that he focused on the COD. Did you consider BOD because BOD is a parameter that measures also biodegradable matter? We know that COD measures both of them, biodegradable and non-biodegradable. But since you talked about the biodegradable matter, which can be measured by the BOD, so if you didn't consider BOD, can you tell me what the reason of this? Thank you.
Thank you very much. Okay, we have one more question there. 2 questions actually, okay.
My question is for Dr. Mohammed. How does the membrane affect the environment in terms of chemical usage, energy consumption, and waste generation?
All right, we take one more question there in the back of the room, then we collect the answers.
السلام عليكم. عياد جنان من جامعة الدوحة. سؤال تو دكتور العبري من جامعة السلطان قابوس. السؤال يعني هم سؤالين في الحقيقة بس you already answered one of them in your future work. So one of the things maybe we need to consider, or I will ask you to probably to have a look on this life cycle, the life cycle of the membrane. So you already presented the cost, but we need to compare so both life cycle and cost. And another one, probably another factor we need to consider, the maintenance. So how that looks like in the future. مشكور جدا على المحاضرة قيمة جدا ومعلومات ما شاء الله جزاك الله خير شكرا. Thank you.
شكرا. Thank you very much. So let's our speakers chance to address these questions and we can come back for another round of questions. Please, Doctor. تفضل.
يعطيك العافية دكتور. بالنسبة حق سؤالك, yes, we have tried to wash and backwash the pipes. However, we can do that with a microbial fuel cell because if we did that, we will distribute all the microbial community attached on the anode. So we can't do anything with a microbial fuel cell. But with the pipes, yes, we did wash and we did the backwash. Regarding the second question, yes, we did measure the BOD. However, due to the time, I haven't shared the BOD concentration, but we did measure the BOD and we did also measure the COD to BOD ratio to understand the biodegradability of the organic matter. If you would, I can provide you with the final report of the research idea and we can share it.
يعطيك العافية دكتور. شكرا. دكتور عماد.
Of course, when we run the business model, we have different and multiple scenarios. It's not only one options. when you conduct usually the feasibility studies, it's based on the assumption. And then we're relaxing this assumption. One of, for example, is the ownership. When it's the government, since we know that all of the source of funding from the government, but when we are talking about the private sector, then we have to run also to assume that the private sector, at least he will receive 12% internal rate of return. Also, we have different scenario of the technologies, different scenarios of the plant size, different scenarios of the coverage. So we will not assume that all of the customer will be involved or will be covered. Also, there is also a scenarios for to look a source from external funding from international donor as carbon credit, different also size of capital cost and technologies. So we're taking into account that we have at least, it was in the study, more than 12 scenarios with different iteration, including risk analysis using risk simulating. So in order to achieve what is the least cost option, so with these scenarios. Yeah, thank you. That's... yes, yes, that's...
شكرا دكتور العبري تفضل.
شكرا مهندس محمد. It's electrospun nanofibers. So it's not technically a membrane, but it's also a membrane, and it's blended with nanomaterials. So it's a one layer, only one layer composite. Yes. Thank you very much for the question. And I don't know if your question is about the membrane itself or the membrane process, so the treatment process. But there are a lot of things to consider. With treatment, membranes, they don't, they only keep the issue, but deflect it to the reject, basically. So whatever, any kind of contaminant or pollutant or any kind of organic, inorganic content, it will be removed from the usable water. It will go to the reject. It will stay. So with respect to any kind of environmental, it's still there. If it has any kind of environmental impact, it will stay there. And that's why with photocatalysis, we try to reduce it as much as possible. Photocatalysis is not capable of removing or treating inorganics most of the time, except of course, a kind of reaction to convert it to something else. So ammonia to nitrogen or nitrates, which is much better to work with. Also chromates and the others. With energy, we have, of course, RO requires a lot of energy. That's why we try in other kind of membranes and other kind of technologies so that we use less energy. RO requires a lot of requires high pressure. That's a lot of energy. When we compare it to capacitive deionization works with 1 bar, maximum 2 bars. So that's a lot of energy saving. But again, we need electrical energy because without the charge, we cannot get the charges at the other sides of both sides of the electrodes. But again, we really need to think about a lot of considerations, and that's why we have to work with the industry, because each plant has its own challenges. And if we don't think about that, and we take it the general and we look at what is in the literature, we are not going to succeed, because the natural part, the area itself, the type of wastewater, what are the contents, what are other considerations, pH, temperature. I've seen plants and worked with plants where a rise in 1 degree Celsius in temperature stopped the whole plant. And of course, we have other things like the algal blooms and all of these things. But this requires a lot of discussion as well. Thank you very much for your compliment. Yeah. If I may, just to answer to my colleague at the back, thank you very much for the compliment. I really appreciate it. And again, really there is a lot of work that is needed to be done. We do a lot of work. I've seen the work in the GCC with many centers and universities. In the Arab world as well, we have worked with many groups and centers. But there is also a lot of things to be done. Membrane recyclability is very important. Tons and tons of membranes are thrown away and we have no idea what to do with them. The life cycle, when we buy it, they tell us, these big companies, they tell you life cycle of 5 to 7 years, and sometimes even they go as high as 10 years. But I've seen membranes that go to one year or 2 years because of how harsh the water content is. RO membranes are very sensitive, extremely sensitive. We always say that they are very good for desalination and all of that, but we need very high water quality to go into the membrane. And so the pre-treatment is extensive. Many steps of pre-treatment to remove everything except the salinity. And even with that, we have reduction in water in the life cycle. And this is why what we want is, even if the membrane reaches end of life, why not take it again and either repurpose it for wastewater, or the idea that we currently have is we rejuvenize it basically so that we have another RO layer at the top for the thin film, and we return it back into the RO plant. And so this will increase the life cycle, will at least double the life cycle of the membrane. And I hope that really we will succeed, because that's very important.
Thank you, Doctor. A lot of obviously of insight to share. So probably it's going to be the last question, briefly, please, because we already used the break time. Do we have a mic here, please? Any mic? No, because I think we have the streaming.
Dr. Mohammed, from our work, we calculated that the energy consumption of RO versus nanofiltration is 1 to 10. Just to support your argument. It's 1 to 10, because the pressure is 1 to 6 and the yield is 1 to 1.5, 1.6. Okay, recovery. So it's about 10 to 12 time multiple. Regarding rejuvenation of membranes, you can do that on the spiral one maybe, but on the hollow fiber, I think it's out of question, right?
But hollow fiber is not used for desalination anymore. Okay. Yeah. It's actually
still used.
So the funny thing is, when I did my PhD 100 years ago, yeah, I remember I read your work when you were in SWSCC, where you were working with the combination of nanofiltration with RO, nanofiltration with MSF, and I said, oh, that's very good. It's really good, and it will save life, the membrane life cycle. It will also reduce the hardness on the water, so that the MSF or even the MED will work for a long period and will require less amount of. And I said, oh, fantastic. And I actually discussed it with many stakeholders, say, why don't we use it for brackish water? Nobody is interested. Do you know why? Because it's actually, we can also work with RO, and then high water quality on the one side, we will mix it directly with groundwater, and it will have the same effect.
No, actually, nanofiltration started in the United States on brackish.
Yes.
That's the history.
And the nanofiltration membranes that we have now are different than what we had in 20 years. We have nanofiltration with very high salinity rejection. That reaches more than 95%.
Thank you.
Yeah, so they are very close to RO.
Thank you very much. Very rich discussion. I really invite you to pursue it in the break. I will not summarize this session, because a lot of insightful knowledge was shared in this session. But the thing that I would like to highlight, which amazed me and made me happy, is that a lot of quality research is under implementation in the region, in the GCC and other parts of the Middle East and North Africa. And by the way, I thank the scientific committee of this conference for celebrating this work and also celebrating other works that are shared during these 3 days. So thank you very much for the participants, for the questions, and also the attention. And please join me in applauding these stars, these researchers. Thank you very much.